Hello friends, this is part 3 of mathematical physics, which is paper c-8 of 4th semester 2023 solution, solved paper of 2023 of 4th semester, Dibrugarh University, BSc 4th sem. And this is my Insta ID. If you want to follow me, then you can follow me. Ozaloikazit123. This is my Insta ID, right? And please subscribe the channel, hit the bell icon, and also share with your friends. Inspire me to create new contents for you. Okay. So in the last part, we have solved up to question number 3. Then today we're gonna solve question number 4, right? So there are 3 questions in question number 4, 4A, 4B, 4C, I think. Okay, so we're gonna solve question number 4, right? And please help me to grow my channel. Okay, so share with your friends. Okay, so now let's start with question number 4. So let's start with question number 4.1. Okay, this is 4.1. So here we need to find a Fourier transformation of this function. The given function 4.1 solution. Here the function f of x is given that 1 by root over 2 pi sigma square exponential minus x minus mu whole square divided by 2 sigma square, right, which also can be written as 1 by root over 2 pi sigma square e to the power minus x minus mu whole square by 2 pi sigma square. We can write this way. So we need to find a Fourier transformation of this. So let me go to the new slide and I'm going to show you how to solve this question. So this is the given function. We need to find a Fourier transformation of this. So here it can be written as 1 by 2 pi sigma square e to the power minus x minus sigma whole square divided by 2 sigma square, right? So this is x minus mu whole square. Okay, so how to solve this question? So we need to find a Fourier transformation of this given function f of x. According to the definition, we should get minus infinity to plus infinity. Then the given function f of x, then e to the power minus isx dx. That's what we should get, right? So here it gonna be equal to minus infinity to plus infinity, integration from minus infinity to plus infinity, and f of x is this. We can put this one instead of f of x. So here you see, so this is our f of x, then e to the power minus isx dx. That's what we can write. So this is our f of x we have used here instead of this, right? So hope you have understood this. Now you see, so here this part is constant part, it can be taken outside the integral. So we can write this here, you see, we can write this one here. Okay, we can write this way. So this part is written, and product of this one and this one, it gonna be equal to, if you multiply, then what we can write integration from I forgot to write the constant part here. So what we will get, we're gonna get this e to the power x minus mu whole square by 2 sigma square minus isx dx. That's what we have got. Now you see, if you take this minus common, then this minus sign gonna be positive if minus is taken common, right? So then let us simplify this part. So what we can do here, so if we simplify that, then what we're gonna get, x minus mu square mu whole square and plus isx. That's what we have here. So and we can do one more thing, just wait. Before we simplify this part, let me do one more thing. So what we can do here, that let us take 1 by 2 sigma square common. So then what we're gonna have, 1 by root 2 pi sigma square integration from minus infinity to plus infinity, e to the power minus 1 by 2 sigma square is taken common. In that case, within bracket we're gonna have x minus mu whole square plus I s x into 2 sigma square. That's what we're gonna have, right? 2 sigma square, so here dx, that's what we're gonna have. So hope you have understood this, right? So now let us simplify this part. Sorry, let me write it clearly. Just wait, give me a second. Okay, so okay, so this is what we have got. Now let us simplify this part. So what we're gonna have, so now let me copy this. Okay, so here if we simplify this, then what we're gonna have, so let's simplify this here. So if you square it, then it's gonna be x square minus 2x mu plus mu square. Then we have here 1 I s x plus 2 sigma square. Sorry, and there is no plus, so we have this one. So from here what we can do, you can see clearly that this 2x can be taken common, right? So then what we're gonna have, x square minus 2x, and if you take that common, then what you're gonna have mu, then minus is sigma square, that's what you're gonna have, plus we have mu square, right? Mu square. So now here you see x square minus 2x mu minus I s sigma square, considering this one as a square minus twice a, considering this part as b, then let us write b square. That means the square of this term, right? So what we have done here, we have assumed that this is a square, this is a, this is b, so we should have b square. That means here b square is mu minus is sigma square whole square, that's what we should have. Then plus, let me write this mu square. Now you see this term is extra, this is not present here, right? So we have to subtract it again. So that's why what we're going to write here, just let me copy this one. So we're going to subtract this one, right? So here we should have right minus. Okay, so hope you have understood this. Now this is in this form, a square minus twice ab plus b square, right? So a minus b whole square, that must be equal to x minus mu minus is sigma square, then whole square. If you remove this bracket, then you should get like get this, just wait, mu, then plus is sigma square, just wait, sigma square, then whole square, that's what you can have, then plus mu square. Now again, if you square this one, applying a minus b whole square formula, then what you're gonna have, just let me write this one on this side. Okay, then you're gonna have mu square, sorry, which is already written here, so there is minus, so minus mu square and minus 2 mu I s sigma square, but because there is minus here, so this minus is going to be plus here, you can see. Then plus, this plus sign going to be minus because of this minus. I s sigma square whole square, and again squaring I, we're going to have -1, so it's going to be plus. So, and s square sigma to the power 4. So let me write it properly, sigma to the power 4. That's what we're going to have. Okay, so here mu square cancels, so we have x square minus mu plus I s sigma square whole square plus 2, let me write the I first, 2s sigma square, then plus s square sigma to the power 4. That's what we're going to have. Okay, so hope you have understood this. So now let me use this result of this here. Let us use this result here. So then what are we going to have? So let me go to a new slide. So the function f of x, Fourier transformation of the function f of x, we had got this one, right? This one. So let me copy this, and here you see I made a mistake here. This should be x only, not x square. So let me write here x only. Okay, so from here to there we have written in the form of a minus b whole square formula, so it should be x minus this whole square, right? So hope you have understood this. So now what we're going to do, if we so here I had made the mu here, so this mu is this one here. Okay, so now let us use this result here. Okay, this is nothing but this one, right? And if you use this result here, then what we're gonna have, this is nothing but the Fourier transformation of small f of x. So let me write the result obtained after putting this result here on the new slide. So we have got this result. Okay, so how we have got this one? Putting this result here, you see this result here. Okay, so we have got this one. So if we multiply this one with this one and this one, then what we're gonna have? Then we're gonna have this result. Just wait. So then we're gonna have integration, 1 by root over 2 pi sigma square minus this integration from minus infinity to plus infinity e to the power minus 1 by 2 pi sigma, 2 sigma only, not pi, 2 sigma square x minus sigma mu, not sigma, mu plus is sigma square whole square. Then multiply this one with this, then here sigma square gonna be cancelled, so 2 gonna be cancelled. In that case, then what you're gonna have? You're gonna have minus I mu s. That's what we're gonna have, right? Then again, if you multiply this one with this sigma square, we're gonna be cancelled. Okay, here we're gonna have sigma square, so then as a result we're gonna have minus s square sigma square divided by 2. That's what we're gonna have, dx. Now this is nothing but, just wait, e to the power this one can be written e to the power this into e to the power this separately. So that's why we're gonna write this is into e to the power, just wait, give me a second, just wait. So we can write this way, right? And this part is constant, so it can be taken outside the integral. So we can write 1 by 2 pi sigma square, this is under root, right? And then e to the power minus I mu s minus s square sigma square, s square sigma square divided by 2. then integration minus infinity to plus infinity. This whole thing can be written this way: e to the power minus, so root 2 sigma x minus mu plus I s sigma square, and this whole thing is square on all this whole thing dx. That's what we can do, right? So now what we're going to do, let us consider, let root over 2 into sigma x minus mu plus I s sigma square is equal to suppose t, and if you differentiate both sides with respect to x, then you're going to have 1 by root 2 sigma, and derivative of x is 1, so we have got dt dx, and that is why dx gonna be equal to dt, just not only dt, root 2 sigma into dt. That's what we're gonna have, right? So in this case here, if you see this relation, from this relation it is obvious that t tends to infinity as x tends to infinity, so there will be no change in the limit. So that's why using this substitutions, right, we can replace this one by t, and we can replace dx by root 2 sigma dt, and doing so we're gonna get this result. Let me write the result on the next slide. F of Fourier transformation of small f of x, that's gonna be equal to, just wait, what we're gonna do, let me copy this one. So we're gonna have this into e to the power minus, that's gonna be t, and let me go to previous slide. So this dx is replaced by this value, then you're gonna have root 2 sigma dt. That's what we're gonna have, right? So hope you have understood this. And as I made a mistake here, actually this part which is within this curved bracket, this part is nothing but t, right? So as a whole it's gonna be t square, right? That's supposed to be t square, because only this part we have considered t here, right? So it should be t square. Okay, so now you see 1 by root over 2 pi sigma square e to the power minus I mu s minus s square sigma square divided by 2. Then again this is t square, that's why this is gonna be even function, so we can write this one here like this. Just wait, let me rearrange it. Let me write the s square properly. This is s square, so we can write this way. Just wait, give me a second. So integration just wait, into 2 into integration from 0 to infinity e to the power minus t square, and this root 2 sigma is taken outside as this part is constant. So just wait, let me write this one here, root 2 into sigma. Okay, so then here we're gonna have dt. So here you see this is nothing but your root 2 into root pi into sigma, right? So this root 2 cancels, sigma cancels, so we have only 1 by root pi, and e to the power minus I sigma s into s square sigma square by 2. Then 2 into value of this integral is root pi by 2. We have already discussed in the solution of the paper 22, okay, c-8 paper of the year 2022. Okay, so if you don't know, let me show you how I have got this one, root pi by 2. Just wait. So let me copy this, let me copy it, just wait. First you remember this one, okay, that integration of 0 to infinity e to the power minus t square dt is nothing but root pi by 2. Okay, so let me show you how. Okay, so before that, first let me write the result. This 2 cancels, root pi cancels, so our answer is e to the power minus I mu s minus s square sigma square by 2. So this is the Fourier transformation of the given function, right? So this is the answer. So now let me show you this one, how we have got root pi by 2. So here you see, this is the result we're gonna show. So here you see, integration from 0 to infinity e to the power minus t square dt, right? So now you see, here we have used actually gamma function according to the definition of gamma function, gamma n, that is 0 to infinity e to the power minus x to the power n minus 1 dx, right? So if we consider that x is equal to t square, then its derivative, if you differentiate with respect to t, then what you're gonna have, dx by dt, that's gonna be equal to 2t. So dx gonna be equal to 2t into dt. That's what we're gonna have. So if you replace this 0 to infinity e to the power, x is replaced by t square, then this x is replaced by again t square, and doing so we're gonna have t into n minus 1, t to the power 2 into n minus 1, that's gonna be equal to twice n minus 2, and dx is replaced by 2t dt, right? That's what we're gonna have. Then this 2 is constant taken outside, so here e to the power minus t square t to the power twice n minus 2 into this t is the power on t is 1, so we're gonna have plus 1 here, that's gonna give you minus 2 plus 1 minus 1 dt. That's what we're gonna have. So let us put n is equal to half now. So gamma half is equal to 2 integration from 0 to infinity e to the power minus t square, then t to the power 2 into half, n is half, minus 1, this half cancel, 1 minus 1, that's going to be 0, t to the power 0, anything to the power 0 is nothing but 1, so we have got this, right? And value of gamma function of gamma half, that is nothing but root pi. So you have got this one in gamma function, right? So if you have no idea about gamma functions, I have made videos on gamma functions. You may go to the playlist, you can check. Now you see, so this is going to be equal to 0 to infinity t to e to the power minus t square dt root pi by 2. So if you bring this 2 here, so hope you have understood this. So here you don't need to show all these things, just you need to remember this result. Okay, so that is what we had used here. Okay, so hope you have understood this. Now let's move on to the next question. So now let's solve question number 4. Actually this one also we have done in 2022 paper. Okay, this question was asked, Fourier transformation of this function n into e to the power minus alpha x square. Let me show you that one, that question. You see, this is the same question, n into e to the power minus alpha x square. So this is asked in 23 as well. So this was 2022 paper, and this is 2023, right? So as we have solved this one already, so I would like to request watch all the videos I had made on this paper, and if you have already watched that, then you must have the solution of this question. So now let's move on to the next one. So here you see, just wait. So let us find a Fourier transformation of this. So here f of x is equal to 1 by 2 pi into a square x square plus a square. That's what we needed to now find a Fourier transformation of this function. Okay, just wait. We need to find a Fourier transformation of this function, right? So now let me show you. Now we are to find the Fourier transformation of this function. So according to the definition of Fourier transformation of a function f of x is that is given by integration minus infinity to plus infinity f of x e to the power minus I s x dx. That's what we will have, right? And this is equal to minus infinity to plus infinity. This part is constant, so it is written outside 2 pi. Instead of f of x, we have to write this one, right? So a square x square plus a square e to the power minus I s x dx. That's what we're gonna have. And here you see that we know that e to the power I theta is cos theta plus I sin theta, right? So therefore e to the power minus I s x, that's gonna be equal to, instead of theta we're gonna put we're gonna put minus s theta, right? That's what we're gonna put, right? So then cos s x minus I sin s x, that's what we're gonna have. Okay, then we're gonna use cos times transformation and sine transformation. Okay, so here we're gonna have Fourier transformation of small f of x, that's gonna be equal to 1 by 2 pi integration from minus infinity to plus infinity a square by x square plus a square. Then this is written as cos sx minus I sin sx dx, right? So using the sum and difference property of integration, that minus a to b, integration a to b f of x plus minus g of x dx, we can write this one this way, right? Integration a to b f of x dx plus minus integration again a to b g of x dx, right? Using this property, what we can write this is equal to 1 by 2 pi, let me write this one outside, and integration from minus infinity to plus infinity, just wait, minus infinity to plus infinity a square by x square plus a square cos sx dx, then minus integration from minus infinity to plus infinity, again a square by x square plus a square sin sx dx, right? So I forgot to write the I, so let me write outside the integral, just wait. So I, so that's how we can do, right, using this property. Okay, so hope you have understood this. So let me separate this one. Okay, so now what we can do here, just wait, let me clean these things, just wait. Right, now you see what we're gonna have here, 1 by 2 pi. So cos sx, this is even function, and here we have square on x, that's why it's gonna be also even function, right? So hope you know the meaning of even function. If a function f of x, it is said to be even if it is equal to minus f of minus x, right? So then it is said to be even function. So if this one is even, this one is even, so as a whole it is even. So in case of even function, we can write 0 to infinity here it should be into 2, 0 to infinity a square x square plus a square cos sx dx. Okay, so that means we have this property minus a to plus a. Suppose integration f of x dx, if it is even, then we can write 0 to a 2 into 0 to a integration 0 to a f of x dx. That's what we can write. So we have used this property. So hope you have understood this. Just wait, let me cut it. So now here you see this is odd function. So this is odd function and this is even. Product of odd and even function, that gonna be a odd function, right? So this part gonna be equal to 0 in case of odd function. In case of odd function, minus a to f of x dx. If it is odd function, then it gonna be equal to 0, right? So that's why, just wait, that's why what we can do, we can write this is 0, because since sine sx is odd function, right? But a square by x square plus a square is even function. Okay, right? So now here you see these two cancel. So what we have got here, Fourier transformation of the function, given function small f of x, that's going to be equal to 1 by pi integration 0 to infinity a square by x square plus a square cos sx dx. That's what we're going to have. So let me copy this and let me go to the new slide. Let me copy the last step. Okay, now let me go to a new slide. This is a new slide here. This is the last step we had got. Okay, so now what we can do, now you see, let us take this part only, now zero to infinity a square by x square plus a square cos sx dx. Okay, let us take this one. So now suppose you have a function f of x, you need to find a Fourier cosine transformation. Then we used to write fc of small f of x, that is equal to integration from 0 to infinity f of x cos sx dx. Here in this case f of x is this one. So that's why we can write this as Fourier cosine transformation of f of x. Let me represent it by fc of s. Okay, capital fc of s, right? Let me just wait. Cosine transformation of small f of x. So let me represent it by, just wait, this is equal to this one, right? So let me represent it by small fc of s. This is the Fourier transformation, cosine transformation of the given function. Okay, so then what we can do here, just let me write these things here. Now let us represent this. So here you see, if you compare with this one, then here this one is small f of x. So let us write this one this way. Just wait. Small fc of s Fourier transformation, that is equal to integration 0 to infinity a square by x square plus a square cos of sx dx. And also let us consider this integral is equal to, suppose I, say let it be I. Okay, so now let me clear these things. Okay, so hope you have understood this. Now if you differentiate both sides with respect to s, that means if you differentiate both sides with respect to s, then what you gonna have? So one more thing, if we take this one as f of s, so we can write this Fourier transformation small f of x is equal to 1 by pi. This part we have taken as Fourier cosine transformation of small f of x, right? So this is the part we had taken according to the definition of Fourier cosine transformation. This is nothing but, if you consider this one as f of x, this is nothing but Fourier cosine transformation of f of x, and which is nothing but small f of fc of s, right? So you have understood this. So now let me clean these things. We can write this one small fc of s. Let me write this one, and this is suppose equation number 1. Okay, so now differentiating both sides with respect to s, then what we're gonna have, derivative of this will be equal to integration 0 to infinity derivative of the given function. So let me write this one here. So what we have, we can write this one here also. Just do it. Wait. Okay, let me keep it this way. If you don't want to assume this side, then also it's fine. Just no need to consider this one. Just this is nothing but what? This is nothing but Fourier cosine transformation of a square by x square plus a square, right? So hope you have understood this. Let me write that way. Okay, so now you see, what if you differentiate this, what you're gonna have? As you can see, we are differentiating with respect to s, and this is the only function of s, right? This is the only term which is function of x, and this is not function of s, this is function of x, and this is function of s. Okay, so that's why what we can write, we can regard this one as a constant part for this derivative, not for the integral. Okay, so then what we're gonna have, integration from 0 to infinity a square by x square plus a square. If you differentiate with respect to s, cos sx, so here x should be taken as constant, and we're gonna write minus x sine sx, right? So here we're gonna have minus here x into sine sx dx. That is what we're gonna have, right? So hope you have understood this. Now let me clean this one. Okay, so what we have got here, you see, we have got derivative of this function with respect to s, Fourier cosine transformation of the given function. Now what are we going to do here? You see, just this x can be written with this a square, right? We can write this way, Okay, so then let me write this one. Then you see minus 0 to infinity. Let mix this x as sorry, let us make this as this x square. Okay, if you make it x square, then you have to multiply x with the numerator and denominator both, then you're gonna get this part, this result, right, dx. So now let me copy it and let me go to the new slide. Just wait. So here is the new slide. Okay, now you see we can write here that minus, we can take this a square outside as this is constant, right? So let me write this one outside, the integral. So let me write this one a square here. Just wait. A square. So this is bracket. So now what we're going to do, we can write plus a square, then again we can subtract minus a square. Then again if you cancel this two, then again you're going to get this result, right? So in the if we do so, then what we can do here, we can write this way. Just wait. Minus a square, just wait, minus a square, integration from 0 to infinity, then we're gonna have x square plus a square by x into x square plus a square sine sx dx, then minus again a square, then we have 0 to infinity 1 by minus a square x into x square plus a square sine sx dx. That's what we're gonna have. Just wait. ds, sorry, not s, dx, right? We can write this way. So now you see here, if you cancel these two, then you're gonna get this. Just wait. So then you're gonna have this result by x. Okay, and we can write this one here. Then if you multiply this one with this, because both constant, then it's gonna be a to the power 4 plus a to the power 4, right? So let me write it correctly. So it's gonna be a to the power 4. Okay, so hope you have understood this. That's what we're gonna have. There will be one, just let me do one more thing. Let me keep this a square as a square. Let me keep this one. Just wait. What we have done here, you see, so just multiply these two, then this minus minus gonna be plus, then just wait, then we're gonna have, just wait, sorry, as we had minus a square, so we can make this one plus, right? So let me keep it this way. Now here you see, now you see here that integration 0 to infinity sine x by x dx, that is equal to pi by 2. So here this one gonna be also pi by 2, right? So that's why we're gonna have ds f of here you see derivative of the cosine transformation of s, that's gonna be minus a square. Here we're gonna have pi plus, we have got this one. Let me copy this. Right, so now again if you differentiate this, right, So if you differentiate it again, then second order derivative of this is constant, so it's gonna be 0 on differentiating it again. So we're gonna have 0 here, a square. Then as we are differentiating with respect to s, this is the function of s, only function of s is this one, sine sx. So here 0 to infinity a square x into x square plus a square. So it's gonna be into again x sine sx dx. Here x is taken as constant, right? So hope you have understood this. So now you see this x cancels, so that's why what we're gonna have, so let me copy this one and let me go to a new slide. So this is what we have, a square 0 to infinity a square by x square plus a square. So on differentiating this, that's supposed to be cos, actually that's supposed to be cos. So here you see, so if you differentiate this sine sx, that should be cos, right? So cos of sx dx, right? So now you see here what we're going to do, a square, this part, if you see, this part is nothing but Fourier cosine transformation, right? This is Fourier cosine transformation of f of x, right? And right or wrong? If you see, let me go to the previous slide. Here you see, this is the Fourier cosine transformation of this function, right? Fourier cosine transformation of this is given by this one. So hope you have understood this. So we can write this is a square into fc of s, right? fc of s, since fc of s is equal to, let's write it properly, integration from 0 to infinity a square by x square plus a square cos of sx dx, sorry, so that should be cos, right? So hope you have understood this. So this is what we have got. Now this is the second order derivative of fc of s with respect to s, right? So we can write this one this way, second order derivative fc of s minus a square fc of s is equal to 0. So here we can write we can write this way, taking fc of s common, we can write this way, right? So this is nothing but a differential equation. We can write this part as capital D square minus a square into this. So now you can compare with this one, equation of this one, x is equal to 0. So differential equation, this is a differential equation, right? So let me copy this one and let me go to new slide. So here you see, this is what we have got. So what going to be the auxiliary equation of this differential equation, that is m square minus a square, just d is replaced by m, and that's going to be equal to 0. This is the auxiliary equation, and from here what we're going to have, m square is equal to a square, which implies m is equal to plus minus a. So these are, so here we can say m1 is equal to plus a and m2 is equal to minus a. So as we are getting distinct roots, okay, real and distinct roots, so real and distinct roots. Therefore CF is C1 e to the power m1 into s. Here the just wait, this one is f of s, sorry, this should be f of s. Okay, now you see, if you compare with this equation that d square minus a square, here y equal to 0, where y is a suppose function of x, in that case it's CF. If the roots, we get those roots, then it should be given by 4 distinct real and distinct roots: C1 e to the power m1 x plus C2 e to the power m2 x. That we should get. But here it is function of s, so we're gonna have here m1 is nothing but here m1s plus, just first let me write it, m2s. So that is CF is equal to as plus C2 e to the power minus as, and here pi is equal to 0, because for this type of equation, as we have 0 here, not a function of x, so that's why in this case pi should be 0. So the complete solution is given by CF plus pi, so that's why it can be equal to, so let me write here CF, we have got this one, C1 e to the power as plus C2 e to the power minus as, and pi is 0 here. So this is the solution we should get, right? So now you see, now go back to previous slides. So here let me go back one more slide. Okay, if you see this one, just wait, this one here, let me take this one as equation number 2. This is suppose equation number 2. From equation number 2 and from equation number 1, this is here you see where is the equation number 1, where I have given equation number 1. So this is suppose equation number 1. Okay, this is the equation number 1. So from 1 and 2, what we can write? So from equation number 1, we have that small fc of s is equal to integration 0 to infinity a square by x square plus a square cos sx dx. So at s is equal to 0, fc of s at s is equal to 0, if you put s is equal to 0, then what you gonna have? So let me write these things in the next slide. Okay, let me let me go to new slide. So these are the things we have got, and from here you see, from here we can write that fc of s at s is equal to 0, we're gonna have, if you put 0, s is equal to 0, then you're gonna have c1 e to the power 0 is 1, then again c2, we're gonna have this. And from this equation number 1, if you put s is equal to 0 here, cos 0 is 1, that's why we're gonna have integration from 0 to infinity a square by x square plus a square dx, and this a square is taken outside, the integral 0 to infinity 1 by x square plus a square dx, and integration of this is nothing but a square 1 by a tan inverse x by a, and here we have 0 to infinity, right? And in that case we should get, if you use the limits, then a square 1 by a tan inverse, here you should get infinity by a, that's going to be infinity, and tan inverse infinity is nothing but pi by 2. Okay, pi by 2, right? And tan inverse 0 is 0. Okay, so a cancels a square, then we should get a pi by 2. That is what we will have. And from this relation we should get that this is equal to c1 plus c2, that is equal to a pi by 2, right? So this is one equation. Then again, from equation number 2, if we take just wait, let me write equation number 2. Okay, now you see one more thing, that just wait, let me have more space here. Just wait, let me scroll down this one. This is S0. Now from here, let me arrange it properly. Okay, now you see, from this, if you find DDS of FC of S, then here if you differentiate it, then what you should get? C1, not only C1 into A e to the power S plus, and sorry, not plus, minus C2 A e to the power minus AS. And again, at S is equal to 0, this should implies DDS of FC of S at S is equal to 0. This should be equal to C1 A minus C2 A. That's what we should get, right? That's very simple. So hope you have understood this. So now here you can see that from equation number 2, let me go back to previous slides. Okay, this is the equation number 2. Here you see, from this one, what you're gonna have. So let me write that one here. You see, just wait, from equation number 2, let me write this one here. Just wait, from equation number 2, what we should get? We get DDS of small fc of S is equal to minus a square pi by 2 integration from 0 to infinity. So here we should have a plus sign, a square sine sx by x square plus a square. That is what we had, right? Sorry, that should be a, there should be x. This one we have. Okay, now you see, at s is equal to 0, at s is equal to 0, DDS FC of S at S is equal to 0. Sine 0 is 0, so that's why this part gonna be 0 at S is equal to 0, right? So that's why what we're gonna have, this is equal to minus a squared pi by 2 only. That's what we're gonna have, right? So now you see, again, this is nothing but equal to this one, right? Right? So what we can write that, now you see, let me go to the next slide. We can write that, let me copy this one first. Here you see this one, we have already got this one. Let me go back to previous slide. This is equal to this one, right? So that's why we can replace this by c1a minus c2a minus a square pi by 2, and in that case dividing each side by a, then we should get this is equal to minus a pi by 2. Again we have already got one more equation. Here you see this equation. So now let me copy this one. This equation that here we have got this. So if you simply solve these two equations, if you solve this one and this one, then what you should get, let us add these two equations. Then minus c2 plus c2, that's going to be cancelled. Then we're going to have c1 plus c2. Okay, let me write this as equation number 3. This is 4. Solving equation number 3 and 4. Then what we're going to have, just wait. If you add these two equations, then minus c2 plus c2 going to be cancelled. Then c1 plus c1 is equal to minus a pi by 2, and there is minus sign, so it can be minus a pi by 2. So this two cancels. Again we're going to have 2c1, that's going to be equal to 0. So c1 is equal to 0. Let us put c1 either here or here, right? So if we put 0, then what we should get, if you put 0 here, then also get same value. If you put 0 here, then you're going to have 0 plus c2 is equal to a pi by 2, which means c2 is equal to a pi by 2. So we have got c2 and c1, right? Let us use those values here. You see, as if we have got this solution here. This is okay. Let me put those values of c1 and c2. Okay, let's put those values of c1 and c2 here. Okay, so then what we're gonna have, here you see, therefore we're gonna have small fc of s. So c1 we have got 0 into e to the power as, then plus a pi by 2 e to the power as. Actually there should be a minus, I think this is positive, here minus. Okay, we should get that one, right? So this part is 0, so if we don't write, then also no problem, we can write simply like this way. So this is what we have got, right? Now you see, let me copy this result and let me go to new slide. So what we have got this one. So now let's get back to the previous slide. Here you see, so I have done one more I made one more mistake. So as I have given this one equation number 1, so let's don't give here equation number. Okay, so just let me copy this one, or you can give this one as capital A. Let me use here capital A. Okay, so that we can write from equation capital A, we can write what we have got. We have got this one, right? So here, Fourier transformation of small f of x. Small f of x is the given function. Okay, so that is equal to, we have got 1 by pi cosine transformation of small f of x. So that is 1 by pi. We have got this one equal to this. Here we're gonna put a into pi by 2 e to the power minus as. That's what we have got. So here pi cancels. So this is our answer, a by 2 e to the power minus as. This is the answer, and this is nothing but, just wait, this is nothing but, so small f of x means, what was small f of x? Here you see, this is the small f of x. Just wait, this is the small f of x, right? So just let us copy this one. So now, so the Fourier transformation of small f of x means this Fourier transformation of this is equal to a by 2 e to the power minus as. That's how we can solve. So this is our answer. So in the next video we're going to complete this paper. Okay, so here you see we have solved question number 4, 3 and 1, and 2 is already solved in 2022 paper, right? 2022. So that's why I didn't leave it here. So in the next video, in the next part, we're gonna solve question of 5 and 6. Okay, that will be completed in the next part 4. Okay, thank you for watching. See you in the next video.